Hey, so yesterday we watched that video of the guy who ran the loop, okay, which is kind of our introduction to vertical circles. Now, the reason we separate the horizontal circular motion from the vertical circular motion is they have some fairly fundamental differences. Okay? Something going around and around in a horizontal circle moves at a constant speed. Okay? Thus we call it uniform circular motion. Okay? The bulk of circular motion is uniform. Right? If I have something going around and around in a vertical circle, what happens to the speed? It varies, yeah. Okay? And if the speed varies, that means the forces that are acting in the circle also vary, which is another fundamental difference between that and uniform circular motion where, again, the forces are constant. Okay? So in a vertical circle, we've got changes in speed, changes in the forces that are acting, not so much the forces, but their magnitudes. Okay? And in some cases, their direction. Right? But it's always the same forces. It's normal force and gravity, or if it's something on a string like this, it's tension and gravity. Okay? But everywhere we go in the circle, those change. Now, where in the circle am I going the slowest? At the top. Okay? Because gravity's been slowing it down. Okay? And how much force do I need to keep this thing in the circle at the top? Like how much tension in the string, I should specify. What's that? In some cases it would be equal. If I'm going just fast enough to stay in the circle, look what happens to the string. The string goes slack. Does that mean I'm pulling on the string at all then? If there's no tension in the string, it's not pulling back towards the center. So what's pulling the object back towards the center at the top then? Gravity. Yeah. Gravity acts as a centripetal force at the top of a vertical circle. It acts as a centrifugal force at the bottom of the circle. Because at the bottom of the circle, gravity is pulling down, as it is at the top. But it just happens that at the bottom, down is out. At the top, down is in. Okay, everyone follow the difference there? Gravity doesn't change. It's the same amount, and it's the same direction. But in reference to the circle, it's different. Okay, and so as a result, at the bottom, this thing is going the fastest, and I have to pull the hardest. Okay? At the top, gravity does all the work for me. Okay? But at the bottom, gravity works against me, and so I have to pull harder. Now, that's if I'm just going fast enough to maintain the circle. If I go faster than that, okay, do I have to pull everywhere? I do. Okay? You don't see any slack in the string anywhere now, because it's going way faster than it needs to maintain the circle. All right? Everyone kind of following me there? So, what this comes down to is that the forces change, but it's still moving in a circle. So if it's still moving in a circle, there's still a net force directed where? If it's moving in a circle, there has to be a net force pointing pretty sure we know this. It's in, absolutely. Okay? The only way I get something to move in a circle is if there's a centripetal force, and that centripetal force is the vector sum of all the forces. It's the net force. So, for a vertical circle, we take advantage of that, and we say that Fc equals the forces in minus the forces out, which is not a new formula. Okay? That's the vector sum of all forces. Agreed? Okay. So there are three situations with a vertical circle that we're going to deal with. Okay? The first one is this one. Going under the top of a vertical circle. That's what we saw the guy run the loop yesterday. Okay? He had to achieve that minimum speed of about 8 miles an hour, okay, in order to get through the circle. Okay? In that situation where he was going just fast enough, okay, we kind of saw that he basically didn't push on the track when he was at the top, right? His leg was very straight. He exerted almost no force on the track because he was effectively a projectile. and he was just following a projectile arc that matched the radius of the circle. Right? So if you're going just fast enough to stay in the circle, you don't push on the track, so the track doesn't push back. So the only force keeping you in the circle is gravity. So if I look at this and I say Fc equals forces in, the force in would be gravity, and there wouldn't be any other forces. Okay? Are there any forces acting out here? Nope. There's nothing trying to push me out of the circle. My inertia might want me to go tangent, but that's not out. Okay? That's tangent. It's different. Okay? It doesn't really affect what I'm doing here. All right, so in that case, I would have Fc equals Fg minus nothing. Now, what if I'm going faster than the minimum speed? Now, I do have a normal force. If I'm going faster than the minimum speed, I am going to push on the track, and the track is going to push back. Now I have two forces acting in. Okay, so my forces, I'd have Fc equals forces in, so that would be gravity plus normal force minus nothing. I have no forces out, ever, in that situation. Okay? Going under the top of a vertical circle, you never have any forces acting out. Okay? Now, you've all experienced this one. Going over the top of a vertical circle. Okay? Every time you leave this school and you go over that speed bump out there, okay, you're going over the top of a vertical circle with a radius of about probably like 6 or 7 meters. Okay? If you go over that really fast, not that you would, okay? I've seen people do it, but not that you would do that because you're all smarter than that and don't want to wreck your cars. Okay? But if you went over that really quickly, okay, how would you feel? Lighter. Yeah, you'll feel a little bit lighter. Okay? Because gravity is doing what it always does, pull down, in this case into the circle, okay? But you would go over the top and lose a little bit of contact with the ground. You wouldn't push on the top of the vertical circle as hard as you would if you were just sitting there. Okay? If you were just sitting there, the normal force and gravity would be equal. Okay? But if I'm going over it, I've got some inertia that's going to give me a little bit of a lift, okay? And that normal force is going to be a little less. And I'm going to feel a little bit lighter. Okay? So in this case, my forces in minus forces out would be gravity minus normal force. Okay? Everybody all right with that idea? What if I went really fast? How would I feel if I went over that really fast, besides anxious that I'm going to destroy my car? Yeah, you get so light that you feel weightless. Okay? If you launch, and I've seen someone do it, okay? If you launch off of that bump, okay, then you're not pushing on the road anymore, are you? Okay, well then, you don't have any normal force. Okay? And so if you went fast enough, normal force would be 0. And you would feel apparently weightless. You're not actually weightless. That's why we say it's apparent weightlessness. Okay? But you'd feel apparently weightless. So something you might want to add to your notes here is just a term that we use. Fn is often referred to as apparent weight. Because you actually don't feel your weight. You only feel the normal force reacting to it. Okay? If you're falling, you have weight, but you don't feel it. You only feel your weight when something else presses back because of your weight. Okay? So Fn is apparent weight, and depending on the situation, I could feel heavier or lighter than I actually am. Right? We talked about this with the elevator questions back in the last unit. Okay? We said if I'm accelerating downwards in an elevator, if I was standing on a bathroom scale, the scale would say I was lighter because the floor is not pushing on my feet as much. But the opposite would be true if it was pushing me upwards. It would show that I'm heavier than I actually am. I'm not, but I feel that way. That's my apparent weight. Okay? And a vertical circle can make you have different apparent weights. It can make you feel weightless, and it can make you feel way heavier than normal. Okay? So if I went fast enough, I could go over the top of the circle and produce a feeling of apparent weightlessness. Okay? All right. The third situation. bottom of the circle, on the inside. Okay, which way does gravity act in this situation? Down, which in this case is in or out? Out, yeah. All right, what's this force? Force normal, yeah. Okay. Not only is gravity pulling me into the track, but my own inertia is causing me to push on the track as well. Okay, and so now I would feel heaviest. Okay, bottom of a loop is where you always feel the heaviest, because it's where the track has to push on you the most. Right? If you were flying in a fighter aircraft, so like in Top Gun, after they dropped the bombs and they did that big climb, okay, that's the bottom of a vertical circle. Okay, that's where you would pull the most G-force. Your apparent weight would be incredibly large. All right, maybe 9 Gs. Okay, so 9 times your normal weight, like an elephant is sitting on your chest. Okay, so that's what happens at the bottom. Now, if I'm just sitting at the bottom, these two forces are equal. But as soon as I'm moving, I'm going to feel heavier than normal. Okay, and in this situation, this would be my force in, and this would be my force out. Okay, everybody all right with that? Okay, so as you go through a roller coaster loop, how you feel changes. Okay, you feel lighter, lightest at the top. Okay, on the inside, okay, and you feel heaviest at the bottom. If you're going over the top, you always feel lighter going over the top. Okay. All right, now, does a roller coaster ever flirt with the slowest speed possible for a loop? Like, would you design a roller coaster where it might go at just enough speed to stay inside the loop? I wouldn't. Okay, and nobody ever does. Because if anything goes wrong, they might not get all the way to the top of the loop. Or worse, they could get stuck there. Okay? There are lots of emergency sensors on roller coasters that engage the brakes, and you would not want the brakes engaged when they're hanging upside down at the top. Okay? So you would never do that. Plus, it's not all that fun. Okay? You're going up this hill and you're slowing down, and it's like, boo, you're going slow. Okay? Roller coasters are supposed to be fast. Okay? So they whip through those loops way faster than they need to stay in them. It makes you feel heavier, it gives you that sense of acceleration and speed. Okay? We once ran a kid through a loop on the Mindbender, and he had the SparkView app open on his phone. Okay? And it just used the internal sensors in the phone, which are actually quite accurate. Okay? He just put it in his pocket and ran the loop, and we saw that at the top of those loops, he was pulling 2 Gs, and at the bottom of the loops, almost 4. Okay? So quite a big difference. Okay, between the top of the loop and the bottom of the loop. Not a huge difference in speed, okay, but a fairly large difference in how heavy he felt, okay, versus top and bottom. Okay, everybody with me on that? Okay. Now, those are the 3 points, okay? Top on the inside, top on the outside, bottom on the inside. Why don't we deal with this one? Can you go under a vertical circle? What'll happen? You fall off, yeah. Okay? You can't go under a vertical circle. Okay? And even if you could, I mean, you could build a roller coaster that worked like this as long as you had what all roller coasters have, which is 2 sets of wheels. Okay? One that clamps on the top of the pipe and one that clamps on the bottom. They all have that. Okay? But you would never design a roller coaster where people went under a vertical circle and hung upside down. Okay? Like this. When I go through this loop, I'm sitting like this, or standing as I draw this person. Okay? In this situation, I might black out because all the blood would rush away from my brain. Where does all the blood go in this situation? To your brain. Okay? That's deadly. There's a difference between the types of G-forces that we can experience. Okay? Positive G-forces are ones that make us feel heavier than normal. Okay? Our body can withstand very large positive G-forces. Okay? Up to like 20, as long as it's not for a sustained period of time. Okay? 9 Gs we could probably withstand for half a minute. Okay? 2 Gs you could withstand that for hours and hours and hours. Probably wouldn't hurt you if you were constantly subjected to that. But if I subjected you to 2 negative G's, it would kill you. Okay? The human body is not designed to have suddenly a whole bunch of really heavy blood rushing into the brain. Okay? What would happen to the brain if I had a whole bunch of really heavy blood rush to it? Are there a lot of really small blood vessels in the brain? And what would they do? They'd rupture. Yeah, it would be an aneurysm, like a stroke. Okay? It's really bad for the human body to be subjected to negative G forces and have the blood go the other way. Okay? And usually what will happen if someone has been subjected to that, they'll have some sort of brain injury as well as eye injuries, because the blood will also go to the eyes. There's lots of blood vessels in the eyes. If you've ever seen someone who's had like a big blood vessel break in their eye and their eye's all red, okay? Like, it's gross, okay? But that's what would happen. Okay? So we don't ever deal with that situation because, well, it's not likely to happen. Okay? A fighter pilot could do that, but they wouldn't, because it would kill them. Okay? But if they were to pull out of a dive inverted, that's what would happen. Okay? Their head would be down, okay, towards the ground, and they would have a red out, is usually what they call it, as opposed to a blackout. Okay? But a red out is not something you wake up. Okay? So it's a big deal. We wouldn't do that. Okay? In that Top Gun movie, they went up like this. Okay, so they did this at the bottom, but then when they went over the top of the thing, they flipped inverted. Okay, that was fine because that was this situation here. They were going under the top of the vertical circle, and they were okay to do that. You just don't want to be inverted at the bottom. All right. Now, why don't we deal with any of the sides? Okay, we deal with the top and the bottom. How come I don't say that position?
So like that thing from Top Gun, if they're going down and their blood was going to their feet, by flipping it and then having it G-forces go upside down, would that like bring it back to like their body?
Okay, so they did this and then they did this, right?
Yeah.
Okay, they were oriented like this, because I won't try and draw a plane and embarrass myself. Okay, they were oriented like this at the bottom, and then this is where they flipped. So this was actually still positive G-forces. Okay, because they were, if I go faster than the minimum speed, remember we said we would get that normal force there. I'd feel heavier than normal. It'd be like going through a roller coaster loop at the top upside down. Okay, the blood's not gonna rush to my head. It's actually gonna rush away from my head in that situation. Okay, so why wouldn't I do this situation? Which way does gravity pull here? Gravity always pulls down. Okay, that's tangent to the circle. It's not in or out. It has no effect, okay, on the centripetal force here. In fact, the only centripetal force present is normal force, and it's equal to centripetal force. That's like a uniform circular motion question. We never deal with that, okay, for vertical circles. So you'll never get a question that's about the side of a vertical circle. Okay, do you have to memorize these situations? You don't. Draw a free body diagram each time. Okay? This is all we're really doing here is a Newton's second law question. Okay? And calculating the vector sum of all forces. In minus out. Right? So you just have to draw it and identify the forces. Okay? Each time. Okay. So this is what we saw yesterday, okay, with that guy that ran the loop, okay, with Damian Walters there, the guy that ran the loop. Okay? I have to go just fast enough to stay in that loop. If I'm going just fast enough to stay in that loop, I don't push on the loop. So if I'm wanting to, what the girl there who was talking about he had to run at about 8 miles an hour, okay? She was calculating the minimum speed for that circle, which is actually a very easy calculation. They actually showed at one point that she wrote this formula on the paper. Okay, what we didn't see was the rest of it. If I'm going just fast enough to stay in the circle, gravity pulls me towards the center. I don't push on the circle, so there's no normal force. Fc equals Fg. Okay, and that's all there is to it. Okay, gravity is providing the centripetal force. This thing is essentially a projectile, okay, that's just following an arc. So, when she wanted to calculate how fast Damien would have to run, she just did this. She multiplied both sides by r, canceled his mass, because it didn't matter, it was on both sides, and square root it. Okay, gravity is probably the most common centripetal force. You would be shocked how often a vertical circular motion question, or any circular motion question really, comes down to this. Fc equals Fg. Okay, like honestly, if you had no idea how to do a circular motion question, writing Fc equals Fg and manipulating would probably give you a 1 in 4 chance of getting it right. That's how often gravity ends up being the centripetal force. Now, I'm not saying that's something you should rely on. I'm saying, like, if you were totally lost and had no idea how to approach a question, you had a 1 in 4 chance that that would be the right way. Okay. All right, so she just plugged in the numbers, okay, for that circle, which was not very big, okay, was maybe twice his height. Okay, so let's say he's 2 meters tall, so the radius would be just over 2 meters. All right, so let's say it was 2.5 meters, just to give it a little room there. Okay, so we'd say V equals 9.81 times 2.5 meters as the radius of the circle. Okay, so 4.95 meters per second. So that would be times 3.6, that would be kilometers per hour. Okay, divide that by 1.6. Okay, so the radius of that circle is a little smaller. Okay, I got 11 miles an hour. Okay, but the circle he was running must have been a little bit smaller than that. Okay. So that's all she did. Okay, was just set those two things equal to each other and solve for the minimum speed for that circle. Every circle has a minimum speed, every vertical circle, okay, has a minimum speed if you're going around the inside of it, right? If you're going over the top of it, is there a minimum speed? Can you fall out of a vertical circle if you're going over the top of it? You can't. The track would prevent it, the surface, the ground, whatever it is would prevent it. So the only place where there's a minimum speed is here, because that's the only place you could actually fall. Okay, you can't fall out of the bottom either. Okay? The track is always going to be there. Okay, so as we said, the speed changes as we go around, and the forces change as we go around. At the top of the vertical circle, we might only have gravity, okay, but we could also have normal force, and that line could be 0. It could be the same, it could be longer, it all depends how fast we're going. Okay? At the bottom of the vertical circle on the inside, normal force is always going to be big. Always going to be bigger than mg. As soon as you're moving, normal force is bigger than mg. Okay? Because here, gravity wants to pull out, your inertia wants you to leave the circle, okay? And so it has to counteract all of that. Okay? So you feel heaviest at the bottom. And if you're going over the top of the vertical circle, okay, up here, okay, then you would have normal force acting out and gravity acting in. Okay, but that normal force is always going to be equal to or smaller than gravity. Because as soon as I get any motion around that circle, I'm going to have inertia that wants me to leave, and I'm not going to push on the ground as hard, so the ground's not going to push on me as hard. Okay? They'd be equal if I was just sitting there, but as soon as I start moving, normal force will start to decrease. Okay? And if I go fast enough, I'll feel weightless because I won't push on the track at all. I'll jump up at the top. Okay? All right, I'm going to show you a video here, and this time I'm going to pause it, how those forces change, okay? Especially as they speed up. Okay? I mean, they made those jumps look really effortless, because they were. Okay? I mean, you have to give a little jump, but you're getting thrown up in the air at the same time. All right, so that is where, okay, this idea of forces in minus forces out comes from. Okay? So depending on where we are in the circle, okay, the forces change, but this is always true because it's really just Newton's second law, vector sum of all forces. We have to have a vector sum that is into the circle. All right, now, did anyone ever play with those little orange Hot Wheels tracks when they were a kid? Okay, this is the real thing. This is real cars going through this thing. Okay, did you have to go fairly fast? You'd think so. But actually, at the top of that circle, you're not really going that fast. Or you don't have to stay in the circle. Obviously, you wouldn't, again, flirt with that minimum speed. Okay? You'd probably come in at 120 and zip up and around that thing as quickly as possible, because if you didn't, you could land on the roof of your car, okay? Which I would have to think would end badly. Right? So everyone kind of follow what we're looking at there? Okay? No matter where I am in that circle, okay, this formula is going to apply. Forces in minus forces out, which, as we said, is not a new formula. It's the vector sum of all forces. Okay, so if we perform that loop-the-loop trick, obviously there is a minimum speed that has to be attained in order to achieve that or stay in that circle. Okay, so if this roller coaster here had a radius of 9 meters, could we calculate the minimum speed for that circle? Okay, this is exactly the same calculation that that girl did, okay, for Damian Walter's loop trick. Okay, she just said forces in minus forces out. She identified the forces, gravity, and that's it. Okay, there's no other forces. The roller coaster's not pushing on the track. There's no forces out. Okay, so we just said FG, and then went mv squared over r equals m times g. Okay, this is something that comes up all the time. Okay, even on a unit exam, a question like this can come up. Right? We're just looking for v, so we multiply both sides by r. The mass cancels. Okay, and we're looking at the square root of GR. Okay, and for this particular roller coaster then, that would be 9.0 times 9.81. Right, this is going to give us about 9.4, I think, meters per second, okay, as the minimum speed. Okay, is 9.4 meters per second all that fast? Not really. On a flat surface, you could easily run that fast. All right, now, some roller coasters obviously take advantage of this, okay? If they've got a vertical loop like this, or even in an Immelman, which is kind of a spiraled loop, okay, they're still gonna have the same forces acting in there. So I'll show you a couple of those here. Lighter as I go over the top. So if I'm in this situation, okay, then gravity pulls down, okay? Normal force pushes up, but if I go fast enough, the normal force will become if I go fast enough over the top, I'll feel what? Weightless, which means the normal force is going to become 0. Okay? It's my apparent weight that I feel. So if I feel weightless, it's not because I am weightless, it's because I'm apparently weightless. Right? And that's what they do in NASA's Vomit Comets. Okay? We watched all those scenes yesterday where they were filmed inside of the Vomit Comet. So I'm going to show you a video here where they actually film a music video inside of one of these zero gravity trainers. Okay, so we've got that possible situation going over the top. Okay, we've got under the top where we've already talked about, and then we also have the bottom of a vertical circle. Okay, and at the bottom of a vertical circle, like they were saying in that video, they were experiencing double gravity. It wasn't really double gravity, but it felt like it because gravity wants to pull them out of the circle. Their inertia wants them to go this way, and so their seat had to push on them twice as hard. Okay, so they felt twice as heavy. Okay, that kind of makes sense to everybody? Okay, so that's what we'd be looking at. Those are the 3 situations that we'll deal with. All right, so we've already done the minimum speed a couple of times. So I would like you guys to try question number 2 here, calculating the maximum radius for a minimum speed of 20 meters per second. Now, where does minimum speed occur again? Top on the inside. Okay, and that's something we have to remember. That's the only place that has a minimum speed. All right, give you a few minutes on that one. Okay, we're talking about the top on the inside of the vertical circle. We're going just fast enough to stay in the circle, so the only force acting is gravity. We're not pushing on the track, and there are no forces out. All right, so FC equals forces in, gravity, minus forces out. There aren't any. Okay, and we're down to this. mv squared over r equals m times g, but we're trying to isolate r this time. All right, so we multiply both sides by r, we divide both sides by m times g, and the m cancels. Okay, and what we're left with is v squared, so that was 20. Okay, divided by 9.81, right, which should give us 40.8 meters. Okay, everybody all right with that? Is that a big circle? It's really big. Okay, I've never seen a roller coaster with a 40-meter radius. Okay, on a loop. That is a big, big loop. Okay, questions on number 2? Okay, I want you guys to try this one. Now we're dealing with the bottom of the vertical circle. We got a bucket of water tied to a rope, and the person is whirling it around with the rope. Okay, so like what I did with the roll of tape, except imagine the bucket of water on the end of that instead. Okay, so they're whirling it around and around in a vertical circle, and they want to know what the tension is in the rope here at the bottom of the circle. So we're looking for this force. Okay, we got gravity acting down. All right, so you got forces in minus forces out question where you're looking for the tension. So at the bottom of the circle, we've got Fc equals forces in, that would be the tension, minus the forces out, that would be gravity. Okay, as that diagram would show. If I am looking for the tension, what do I need to do with gravity? Add it over to the other side. All right. Now that makes sense because the tension has to overcome gravity and then act as a centripetal force. So it needs to be bigger than both of them, or be the sum of the two of them. Okay, so we would have mv squared over r plus m times g equals the tension in the rope. Right, so we will have then 1.5 kilograms times 3 meters per second, but v is squared, okay, divided by the radius, which was 0.75 meters, plus 1.5 times 9.81. Okay, so there's my centripetal force, 18 newtons, plus my force of gravity. So the tension in the rope must be 32.7 newtons. All right, everybody okay with what I did there? All right. That's a pretty typical question. Occasionally I might ask you, give you the tension and ask you to calculate the speed or the radius or something like that.
Are you going to have to use vectors?
If it's centripetal, if it says calculate the centripetal force, unless it specifically says magnitude and vector, because it's centripetal, its direction is implied. Right, so if it says calculate centripetal force, it's in. And for tension, tension is just how tight the rope is. I don't give a direction on that. If it asks which way is the rope pulling, you could say up or in. Either one would be right in that case. Yeah? Okay, questions on how that one worked?
Shouldn't the 1.5 times 9.81 like be in brackets if you when you put it in the calculator?
Nope, because I was using the answer function, and then order of operations says I would multiply those two before I added it on.
Oh,
Yeah.
I usually do that.
You can, you know what, if you put it in brackets, it's not gonna do it wrong,
Okay.
right? It's just in this case, I didn't have to, because I knew it would multiply before it added. Yeah. Okay, then. Let's say we're looking at number 3. So we got a rock attached to a rope and spun in a vertical circle. Tension in the rope when the rock is at the top of the swing is 79 newtons down. Okay, what is the speed of the rock? So we are dealing with that situation. Okay, that's at the top on the inside. Something attached to a rope can never go over the top of a vertical circle. Okay, it is always going under the top. All right, give you a few minutes on that one. That was exactly what I said. I might ask you, give you the situation, ask you to calculate the speed instead. Okay, this one is about as, let's say, tricky manipulation-wise as it gets.
let's have a look at this one. So we've got going over the top, which means there's tension in the rope. Okay, and what else is pulling in? Gravity, yeah. Okay, are there any forces out? Not in this case, okay? There's nothing that's trying to directly pull this thing straight out of the circle, right? So what we have then is Fc equals the forces, plural, in, that would be gravity plus the tension minus the forces out, which there aren't any. So this is what I'm left with, okay? Now, that means then that tension can be smaller in this question because it's got gravity helping it out. So it won't be like when we were dealing with the bottom where tension was very large. Okay, tension doesn't have to be as large in this situation. So if I'm looking for the speed of the rock, that's part of Fc. So I want to plug in my formulas. mv squared over r equals m times g plus t. Now, if I'm going to manipulate this for v, I need to first multiply both sides by r. But that means I need to enclose this in brackets because it was over there first. And I'm bringing something over and multiplying by that side. So I need to make sure I do that side first and then multiply by r. Okay, so now r is over there, and now I'm going to divide both sides by m. M is not going to cancel here because it's part of that side, and there's an addition operation in there. All right, so this is why I'm saying this is kind of a tricky manipulation. That solves for v squared, so I've got to square root that whole thing to get v. So v will be the square root of m times g plus t times r over m. Okay, so when we're plugging in all of our numbers here, that's going to be 0.98 kilograms times 9.81 plus, okay, the tension, which they told us was 79 newtons. Right? And then we're going to multiply that by the radius, which they told us was 0.4, I think. Yeah. And then we're going to divide that by the mass, 0.98. Okay, so it's, like I say, it's a tricky manipulation on this one. So 0.98 times 9.81, there's my force of gravity, plus 79, the tension. Okay, multiply that by the radius, 0.4. And then divided by the mass, 0.98. Okay, that's v squared, so I got to square root it. And I'm looking at 6 meters per second for the speed of that object moving in that circle. Okay. On a unit exam, every year I change where in the circle the vertical circular motion question will be. Okay, sometimes I ask going over the top, sometimes I ask one like this where it's under the top, sometimes I ask the bottom of the vertical circle, okay, but there's always a vertical circular motion question on the exam where you're going to have to go forces in, minus forces out, and solve for something. Okay? All right, questions on that one? Okay. Tomorrow, we're doing a lab on centripetal force and speed. Okay, so we're using the tubes again, the rubber stoppers and strings and all that, so that's tomorrow. Okay? Friday, we'll do more vertical circular motion. We'll see how that goes. Monday, we could be doing the assignment on circular motion, which would mean the unit is about a little more than half over. Okay? So on that note, your unit exam is May 29th. We will be done the unit before then. Okay, but that's the week of like May long weekend and all that kind of stuff. I didn't want to mess around with that date. So we'll probably start the next unit before that, but that's when the exam will be, so you can put it in your calendar. Okay? All right.